control. And then we'll briefly go into how the analysis of experiments is related to those 3 C's and to the design in general, how some of the properties of statistical testing contribute to the need for a good experimental design, right? And then we'll wrap up. I'm going to try to make this session a little bit interactive, right? Even though we are a group of 55 people I see now, so discussions can happen, right? And at no point hesitate to interrupt me if you have questions, if you want to contribute with a comment or something like that. I'm always open to that, right? So never hesitate to do that. You might raise your hand or you might just ask our question, right? But I also built into this session some slides that allow you to share your ideas, all of you basically at the same time. So I used WooClap to do that. You see here a QR code that you can scan with your cell phone. And then you end up at a page where you can contribute answers to some questions that I will ask. Right? You can also just go to WooClap and put in the event code that you see here on the screen. Let me make that a little bit more visible, like this. So this is the event code that you can use. I see that 13 people are already registered. 14, 15, 16 is going up. So I'll give you a couple of seconds. Sorry?
It will go up soon.
Okay. So maybe a first question that I would like to ask. I'll give a couple of seconds more so that people can register. So that you still have the QR code and the event code. Okay. So first question that I would like to ask you is, what is your idea about experiments, right? What comes to mind when you think about experiments? You only have 30 seconds to answer, right? So you need to be quick. You can give multiple answers if you're quick. A lab, practical knowledge, research, finding solutions, hypotheses, yeah. Objective, okay. Controlled, very good. Yeah. Okay, so the vote closed. We have a nice cloud of words here that I think are all very relevant. Trial and error, a process, objective, indeed. Well, that's at least the goal, right? To come with objective knowledge. Finding a solution, yes, if the solution is about understanding a process, right, and that's another word that is on the screen. Validating hypotheses, definitely, it is a research method, right? And so the word research is also relevant. And then controlled is very important, and so I will discuss control as one of those 3 C's later, right? So that's good. I think we're on the same page. What I wanted to avoid is that you think of experiments as something like this, right? Which is also what experiments are about, right? Experiments are very often used to discover things, to discover knowledge, but then we're talking more about chemistry and physics and domains related to that, maybe biology also a little bit. What you see, by the way, here is devil's toothpaste, right? That's what it's called. It's a chemical reaction, of which I don't know the details about, I must admit, but it's interesting to watch, right? And so experiments can definitely be about throwing things together and seeing what comes out of it, right? Now, that's very interesting, but not very interesting to data scientists, right? It becomes more interesting to data scientists if we have outcomes that we can predict, first of all, and that we can measure, second of all, right? Because if we can measure those outcomes, then we might be able to do statistical analysis on them, right? Here, there are opportunities for statistical analysis, right? How high is this thing going, for example, depending on the ingredients that you put in, what kind of color comes out, things like that. But that's not straightforward, right? It's more about the effect that you're creating and the new substance that is the result of throwing together other substances, right? So that's experimental research that is not my terrain, right? And that I will also not further discuss. But it's interesting to know that there are these two notions of what is experimental research. So what experimental research is to me, and for the purpose of this session, is a research method, right, in which a researcher or more than one researcher intentionally varies some aspect of the environment in which there are certain subjects that are that are being observed, right? And the manipulation is done to investigate that manipulation's effect on some focal outcomes, right? So what is important to specify is that you can have several manipulations going on at the same time, even though you have to be very careful with that to make sure that you still know what you're doing, right? And that you can also have several outcomes that you investigate at the same time. So what we intentionally manipulate in a situation is very often referred to as the independent variable or the manipulation, can be multiple ones. And what we investigate as focal outcomes, the effect on these focal outcomes, is very often specified as the dependent variables, right? Especially if we talk about that kind of experimentation that is interesting for data scientists, right? If we talk about chemistry and putting substances together, then we might not be so interested in independent variables, right? Then we might be interested in other things, in effect, in explosions, in things like that. But if we talk about outcomes that we can measure, then we can discuss those as dependent variables, right? So experiments are used in many different domains all around us, right? We might know them very well as related to
Good evening, all of you.
medication. Excuse me? Was that a question or? No, okay. We might know them as related to testing medication, new kinds of drugs, right? To see whether those drugs actually work and have an effect on curing some kind of disease. Experiments might also have to do with physics, right? We might measure the resistance of air, for example, when objects travel to them and through them, and that resistance might depend on the air pressure, for example. So we might manipulate and vary different circumstances to see what that does on objects traveling through air or on light traveling through a kind of space, things like that, right? All of these things might be tested with experiments. We might also think of experiments in the context of psychology, right? How people visually process information, for example, how different circumstances lead them to put more weight on different aspects of making a decision, etc. So this is something that that I'm especially occupied with because I have a background in consumer research, right? And consumer research relies heavily on psychological methods and effects, and so we apply a lot of psychological principles in studying consumers, for example. Right? Experiments are also done in biology, right? Seeing how living species react to different circumstances, for example. Experiments are also done in agriculture, right? Seeing which kind of fertilizer yields better crops, yields more resistant crops, more resistant to diseases, for example. And what you see here is that to run an experiment like that, it's important that you vary this this manipulation, that you try out different types of fertilizer, for example, or that you compare to no fertilizer, right? Which is something that we will discuss later as well. Experiments are done in sociology as well. They're also definitely done in business contexts, right? HR or theory about HR, for example, relies heavily on experiments, and also research on HR relates a lot to psychological research as well. And so we might look at the influence of team composition on performance, for example. We might create different teams with more balanced teams, for example, in terms of hierarchy, in terms of experience, for example, or teams that are more specific, or teams that are more balanced in terms of gender, right? This could be the topic of research. Teams with specialized knowledge versus generalist knowledge, etc. Right? All of those things can be studied. All of these manipulations, all of these changes to the teams can be studied in their effect on performance, on well-being of the team members, etc. Right? And then experiments are definitely also a part of research about marketing, where we can look at, for example, changing prices up or down, to what extent this affects people's likelihood of buying, right? In a very simple setup. We can also look at how people's perception of those prices changes as a consequence of changing them. Whether people see differences in prices, right? There's research showing that you have to that discounts need to be substantial before they create an effect, for example. We can also look at experiments in the context of technology, right? A/B testing is a concept that you might have heard of, that you might be familiar with, and is a process of optimizing websites, for example, where part of the visitors of a website are selected to see a different version of the website, and then the outcome that is investigated is whether people stay longer on that website, whether conversion rate is higher for that different version, whether people enjoy that website more, etc. Right? And this can be done automatically, and while the website is running, so this can be done live basically, and changes can be made live as well. And so this can be part of a continuous process of improving or of optimizing that website. Right? So experiments are all around us, sometimes without us knowing, right? And they're used in many different contexts. What is important to distinguish as well is that experiments, I think somebody mentioned lab experiments, right? In the word cloud. Yes, experiments are very often run in a lab. They're also sometimes run in the field, as we say. So that means that they are run in a realistic context, right? So, for example, if we talk about these experiments about price, we can do those in the lab to see how people react. We can also go to stores and actually change prices and see how this affects sales, right? That would be the difference between a lab experiment and a field experiment. There are different advantages and disadvantages to both, right? Which I will go into later as well. Some obvious ones are that in a field experiment, you have more realism, right? You are testing something in the environment in which a phenomenon naturally takes place. But that means that this environment is also very noisy, right? That you have lots of external influences and potential disturbances on that phenomenon as well, right? So the findings or the likelihood of finding an effect in such an environment is lower, right? It's more difficult to do that. So going further to those to this A/B testing, for example, this is how that could look like, right? You could split up 50, or you could split up the visitors of a certain website into equal halves, and then half of the visitors see this version with a light blue background, and then the other half sees a version with the dark blue background. And and you what you investigate then is whether this affects conversion, for example, right? And if you see that conversion is much higher with the dark blue background, then you might decide to switch your website to a dark blue background for everybody, right? Because apparently this leads to better results, right? Now, there are some potential problems with that, right? For example, or some potential challenges. For example, you need to know when a difference is big enough, right? And you all have a background in data science, so you hear me coming. This involves a statistical testing, right? There will be some random variation on those conversion rates throughout the whole process of testing. And we need to be sure that any difference between those two versions is not just due to chance, right? What we also need to be sure is that it's really this change in background that caused the difference in conversion rate, right? Because there might be multiple potential explanations for that difference. Maybe you run 50% of the visitors that see the light blue background. Maybe you run that part in the morning, and then the dark blue background in the afternoon. And maybe in the afternoon, people are more ready to buy, right? So you need to be sure that there are no other explanations for any effect that you find, right? And so what experimental research is very good at is finding causality, right? Meaning that you find the cause of a certain outcome, right? But a condition for that is that your research is very well designed, right? That there are no flaws in the way that you set up your experiment, because if there are, then this causality is undermined, right? And causality is really what we're looking for in experimental research, right? And this is a big difference with other research designs, right? For example, with cross-sectional data, it is much more difficult to conclude or to make conclusions about causality, right? If data points for, even if you talk about different groups, right? Even if you analyze a group of people that have seen a light blue background of a website and a dark blue background of a website, even if people have seen different versions, it's difficult to conclude that any difference in behavior afterwards is due to those changes if that data was not collected in an environment that was really controlled as an experimental setup, right? So cross-sectional data is has its benefits, right? But it's difficult to conclude about causality based on cross-sectional data. I see that there are some questions in the chat. Let me switch to that to see whether these are things that I need to answer. Okay, so these are these are mostly practical questions, and then nuclear fission. I don't know what you mean by that, but it's an interesting comment. Okay. Let me close that. So as said, don't hesitate to ask if you have questions, right? Also in the chat, you can do that, and I'll try to regularly stop and see whether there are questions there that I should answer, right? So causality is the main focus of experimental research, right? And it's very important to realize that your experimental design either helps finding causality or destroys the possibility of finding causality, of concluding on causality, right? If your experimental design is poor, then no statistical analysis can save your conclusions, right? Rubbish in means rubbish out. If your statistical design, for example, did not control for certain circumstances, and therefore these circumstances differ between different groups that you create in your statistical design, then we will never know for sure whether any difference that you find was due to the manipulation or due to those differences between the groups, right? And there's no way of finding out afterwards. So a good experimental design is a condition for finding solid statistical conclusions, right? I again see that there's something in the chat. No, okay. Or yes, right. I was scrolling. Okay, what are some methods to reduce noise in field experiments? Well, that's an interesting question that I will keep, right? I'll come back on that if that's okay, right? So it's important to make sure that we have a solid design to find solid conclusions, right? So what do we need to think about when we think about experimental design? Well, there are a couple of things that we need to consider, which is first the independent variable, the treatment, then the outcome that we're studying, and then subjects that we are including as units of observation in our experiment, right? So let's go over these three. The independent variable is a variable that is being manipulated by the researcher or team of researchers, right? So this can be the presence or the absence of something, an amount of something, or a type of something, right? In general. What is crucial is that it is something that is subject to being manipulated, right? Because some things we cannot manipulate. So very often we can read scientific work where the independent variable is something like age or gender or personality or culture. And what is important to realize is that these kinds of designs that include independent variables like that are limited in their conclusions, right? Or that you have to be very careful with interpreting their conclusions, because by definition or by their nature, variables like that are not really subject to manipulation, right? We cannot manipulate the person's age. A person's age is what it is, right? If a person is 40 years old, then you cannot make that person 50 years old, right? If a person is male or female, then this is something that as a researcher you cannot change, right? Personality variables, same problem. You cannot make an extrovert all of a sudden be an introvert or things like that. Cultural differences, same thing, right? You might try to imagine what it is to be, I don't know, a person from the UK or something like that. But imagining is not the same as being, right? It is a proxy, right? All of these variables, to some extent, can be approximated in some way, or they can say something, right? So they're not useful. Not useless as variables. That's not what I'm saying. But when interpreting the findings, we need to make considerations, or we need to keep open the possibility that we are not actually testing the effect of age or gender or personality or culture, but of a variable that is strongly correlated with age, gender, personality, or any of those other variables, right? We need to be very careful with our interpretation of the findings. to make sure that we are not missing an explanation for these findings, right? If we then look at dependent variables, these can be ideally, this is overt behavior or other kinds of outcomes, either of people or of crops. If we talk about experiments in agriculture, for example, things that we can readily observe, right, and interpret. But we can also think about verbal reports or questionnaire responses if we talk about people, physiological differences even. All those could qualify as dependent variables. And what is good to consider is to include multiple dependent variables, right, that are related to each other in some way. So if we talk about psychological research, for example, and we measure people's excitement, it might be a good idea to use both skin conductance as a physiological method and questionnaire responses, right, to kind of have a double measure of the outcome of our study. And what we can check is whether those two dependent measures correspond to each other, confirm our findings, and confirm each other, right? And we can ask for verbal reports at the same time, right? So we might use several dependent variables to test for the same thing, which is excitement, for example, right? If we then look at the subjects or the participants that we can consider, so this is the unit of observation, basically, that participates to the study. We can think about individual people. We can think about households. We can think about stores. We can think about companies. We can think again about crops if we think about doing experiments with different kinds of fertilizers. We can also think about different farmers or farms. Basically, the unit of observation is the unit of analysis as well, is the unit that is included in that experiment, and is usually selected because that unit is part of a sample that is considered representative of the population that we study, right? You all have a background in statistics, so I won't go too deep into that, but I do want to underline the importance of having a good sample that is representative of the population that you study, right? Otherwise, you start up with a flawed design, and your conclusions will not be very valid, right? Or might be biased based on a biased sample, right? So these are three things to consider about the design of an experiment, and then three different things or three points of attention that I want to raise are about causality, comparison, and control, right? As mentioned at the start of this presentation. So let's go into these three different topics, right? Causality is, as said, what experiments try to find causal effects of the independent variable on the dependent variable. And it's very easy to make mistakes about causality, right? People are kind of used to seeing causality in many different places, even if there is none, right? We try to understand the world around us. We try to make sense of that world. So we try to relate phenomena to each other, right? That's what we do all day, basically. And it's because of that tendency, it's also very easy to see causality in our findings, even if there is none. So one thing that is important about causality is that a cause affects an effect, right? And that it's not the other way around. So what is important in causality is the direction of an effect, right? There needs to be an effect of the independent variable on the dependent variable, but not the other way around, right? And the reason why it's not the other way around can be found either in theory, right, in logic as well, or can be found in the order of things, right? So it's important that there's covariation between the cause and the effect, but that there's also temporal precedence of the cause before the effect, right? If you find that it doesn't matter which comes first, the effect or the cause, then it means that there's no causality, right? Then it means that there's just covariation, and that there's actually no effect of the cause, right? That the effect can even influence the cause as well, right? And what is also important is that you exclude other potential causes, right? And we will discuss that later as well, as control that you need to have, right? But so causality is important to understand in the course of, or in the context of your experiment. And so you need first of all theoretical reasons why the independent variable is the independent variable and is not a dependent variable, right? But you also need to find that the order of occurrences matters, right? That you first need the independent variable, that you first need to manipulate that independent variable before you see an effect on the dependent variable, right? And that this effect is not explained by other variables. And so this is challenging to many researchers, and lots of mistakes are being made with that, even by experienced researchers sometimes, because sometimes the difference between what is causal and what is not, and what is correlation, is very subtle, right? So to see how easily we can see, oh no, there are a couple of other questions in the chat. Let me have a quick look.
Yeah, in fact, there are many. So
many,
do you
okay,
want us? Yeah, do you want us to read it for you, Bud? We can read that.
No, I'll have a look. So how can we differentiate between A/B experiment in digital marketing and data science? How the manner of experience changes in different fields. So the manner, the way that experiments are being run does not change that much between fields, right? There are some core principles that are always important, of some of which we are discussing here, right? And so, by the way, data science, I think, is not a field that is completely separate from digital marketing, right? Digital marketing relies a lot on data science to make conclusions. And so the tools and techniques that are part of data science are adopted by digital marketing to make conclusions about their field, right? To what degree can a researcher deduce the measure of approximation induced in an experiment? How do we extract information from? So these are two different questions, I think. So what we talk about when we talk about approximation is to some extent construct validity, right? Sometimes we cannot help but approach or approximate a concept or a construct because we cannot directly access, measure, or manipulate that construct, right, or that concept. It is important to have valid results. It is important to be as close as possible, right? And one technique of doing that, so I already mentioned that it's sometimes useful to have several dependent variables. This is one way of making sure that we get closer to the concept that we are trying to measure, right? If we think about excitement are many things, but if we triangulate on that concept by using several measures of that concept, and all of those measures show us the same effect, then we can be more sure that we actually are measuring the right concept, and that we actually are finding an effect, right? So triangulation can be part of that. Trying to measure a concept or a construct by using several measures at the same time, and checking whether all of those pointing to the same direction in terms of effect, for example, right? How do we extract information from? By the way, I hope that these answers are somewhat satisfying. If I misunderstand the question or something like that, let me know, right? How do we extract information from independent variables that are intangible in nature? For example, someone's experience in traveling to a certain place and determine how appropriate it is. So I don't really understand the last part, but about the first part, yes, some things are extremely intangible, right? Obvious examples exist. If we think about intelligence, for example, right? Intelligence is something that we all understand, and yet people have different interpretations about it, right? And there are different ways in which intelligence manifests itself. So what we need to agree on is how we measure intelligence, and this agreement is done in research, right? By developing scales, for example, that are then tested against other concepts. Now you were talking about independent variables, right? So again, yeah, we need scientific agreement on what a certain manipulation is. If we talk about experience in traveling, so can you make that a bit more concrete? I don't know who this was. Kriti Srivastava.
Yeah, we can unmute for supporting. Can you unmute so that they can interact and she will ask, she will clarify her question.
I didn't understand the last part. Sorry.
Hello, good evening, Sam.
Hello. Yeah. Okay. So yes, you can unmute, and then so can you make it a little more concrete? What your question is about?
Yeah. So what I basically mean to ask is, like, for example, I'm traveling to a certain city, and when you ask me how my experience is about the traveling from A to Z of it, from the accessibility to all the amenities I've got there. So when it comes to experimental data, most of it is in numerical form, right? Quantitative form rather than a qualitative form. So what I mean to ask is, if there are independent variables that are quite qualitative in nature, like services, experiences, how do we turn them into quantitative data, and we can determine how concrete the approximation in that turning transformation of data is? How do we determine that?
So if I understand the example correctly, then what you're talking about is measuring that experience, right? Which means that the experience is actually the dependent variable and not the independent one, right? Independent variables are quite often qualitative in nature, right? We can create qualitative differences between different groups of people or different groups of stimuli that people are encountered with. The most obvious example is we can give people a drink with different colors, right? And color is a qualitative difference. And we can see how this affects the taste that people experience, right? But that taste is then could then be quantitative, right? Could be a rating scale between 0, very bad taste, and 10, excellent taste, something like that, right? And so if your question is about that experience, then many skills are being developed to translate something that at first sight could be seen or intrinsically could be seen as qualitative, to translate that into something that is quantitative, right? So many different, like literally thousands of scales exist to measure people's experience in different contexts. And those results are then quantitative, right? Because it's true what you say, absolutely, that dependent measures need to be quantitative in some way, or we need to translate them into something quantitative. Is that an answer to your question?
Yeah, pretty much that answers. Thank you.
Okay, perfect. Brijesh, I'm not sure how to pronounce your name, sorry. The variable in experiment with product, for example, price may lead to effect in business. Yeah, so that's that's important, right? If you do a field experiment, then it's important that you consider the potential consequences, right? Because once you change a price, for example, it changes people's price image permanently, right? And so this is something that that entails risks, right? Which is also why store owners and brands might not be very willing to experiment a lot with the way that they do their marketing, right? And so what might be much safer is to first do an experiment in a lab in a more controlled and contained context. And then if you find the effects that you want, that you hope for, to only then deploy them in a larger context. Something that is also quite often done is to work with a sample of stores, for example, right? If you want to test a price change, big retailers do that when they have a chain of stores, to select a couple of those and do kind of a pilot experiment and do that experiment on a small scale with a couple of stores before they roll out a change throughout the whole chain, right? So that can be a way of making that safe for the business, of limiting the impact if it creates undesirable results, right? Mathematical interpretation can be done through a function and variable example. That's true. I don't see a question in that. I don't see any other questions, I think. What are factors which we should consider while excluding other courses? The most important factor is their potential effect on the dependent variable, right? The more a factor is potentially... That's okay. The most important factor to consider for excluding other variables is their correlation, covariation with the dependent variable, especially, but also potentially with the independent variable, because through their covariation with the independent variable, they might create an indirect effect on that dependent variable, right? So the more related a variable is with an outcome, the more important it is to watch that variable and to consider it in the interpretation of your results, right? Okay, let's continue, right? So I was...
I do have one question, actually. It's not a question, it's something doubt I'm having. So if you
have a doubt,
if you take a dependent variable and independent variable, right? So
yes.
the selection of dependent and independent variables might be depend upon the condition as well, right? If I'm doing some experiment, right? So in that condition, like temperature is not important for me. So I think it is not acting as a dependent variable. It's something like an independent variable acting for that particular condition. So I think this way of thinking is right for dependent or independent.
So I didn't understand your second sentence, but what I understood is that it's kind of you indeed have traditions in what is considered a potential cause and what is not, right? That was what you're saying, right? Yes. And so what you definitely need to do before running an experiment is consult the literature, right? To find out about those traditions, those potential causes that people consider, and then potentially make a contribution on that literature by including additional causes that people have not considered yet, right? That's what experimental research is about a lot, right? Finding additional causes or finding additional explanations for phenomena, right? Definitely. Do we also care about an experiment being ethical? We definitely do. And the reason for that is I need to actually go back a couple of slides and emphasize that, is in the potential for harm that is in manipulating subjects, right? So especially if we talk about manipulating the environment of people, some of those manipulations might be stressful, might be disturbing, might be harmful, might have even long-lasting effects, right? And this is definitely something that we should consider, whether the potential benefits of running that experiment outweigh the potential harm that the experiment might create, right? There are famous examples of experiments that turned out to be pretty stressing for the people that participated, right? If you are familiar with the Milgram experiments, where people were put in control of a device that administered electrical shocks to other people when they gave a wrong answer to a question. Now, those shocks were not real, right? But even without those shocks being real, the impression that they were real was quite disturbing to the participants, right? So this is an example of how experiments can be about psychological effects that might impress people a lot, right? So yes, definitely. Stanford Prison Experiment, definitely also. Yeah. So these are things that needed to be ran at some point to come to the conclusions that they facilitated, right? But once you have those conclusions, it might be very unethical to then rerun those experiments constantly, right? That's not something that we want to do. So the fact that we didn't know the outcome and that, for example, for the Milgram experiment, those outcomes are important and explain a lot about why people did the atrocities they did during the Second World War, for example, because that was the inspiration for those experiments. So that knowledge is important, right? But once you have that knowledge, before you didn't have the knowledge, right? You had no idea how people would react. So you could also not foresee the negative effects on people. But once you know, it's important that those paradigms, those ways of running an experiment, those setups are used very carefully and only sparsely, right? That we don't use those setups constantly because we know that they potentially harm people, right? Now it turns out that for the Milgram experiment, the effects were actually reasonably okay, right? Even though people were surprised of themselves, right? Those people were followed up, and debriefing people can be important with experiments. Explaining what the setup was about, right, can be an important way of mitigating negative effects. And in some cases, for example, for the Stanford Prison Experiment or for the Milgram experiment, it's important to follow up with people, right, to check maybe a couple of weeks or potentially even months later how they are doing as a consequence of or potential consequence of participating to that experiment. So yes, ethics is definitely an important topic as well. Yeah. Thank you for contributing in that, because I should have mentioned that in the manipulation at the manipulation slide, but I didn't. So I was talking about the potential confusion between causality and covariation, right? And we are quite sensitive to that. Now, I have a small illustration of that. A text here about a drink that turns out to be very dangerous, right? So you are about to learn of a beverage so dangerous that we must ban or restrict its sales, or at least enact tax penalties on it to deter consumption. Here's what research shows. Every Indian person who drinks it dies. It's been linked to obesity. In fact, bigger people drink the most of it. It's associated with type 2 diabetes, and all diabetics drink it in especially large amounts. All heart attack victims drink it, and it's a known factor in heart failure. And hundreds of studies show that, right? Now, all of these things that I just told you are true for this beverage. My question to you, what is the beverage? We're again going to do this word clouds where you can basically submit your answers. You guys are not fooled easily, right? Other people administering water. Also, some people saying it's Coca-Cola. Alcohol, yeah. Coca-Cola. Milkshakes. Sweet drinks. Caffeine, I see. Soft drinks. Tea, urine. Yeah, definitely. Yeah. No, so the correct answer is was the first answer, right? The correct answer is water. Let's go back to that description, right? Every Indian or every American, it says here, every Indian who drinks it dies. Well, that's true, right? But that doesn't mean that water is a cause of dying, right? It's just two things that are true at the same time, right? Every Indian who drinks water dies because every Indian dies at some point, right? And almost every Indian drinks water as well, right? It's been linked to obesity. In fact, bigger people drink the most of it. That's also true, right? But it doesn't mean that water is a cause of that. It just means that bigger people drink more, right? And they also drink more water. And the same is true for diabetics. And all heart attack victims drink it. Well, that's because almost all people drink it, right? So water is the correct answer, right? Showing you that correlation is not the same as causation, right? Things can go very, very strongly without causing each other, right? And that's important to realize. And this is, of course, a very obvious example. There's also these examples like the higher the amount or the higher the number of firefighters, the more severe the impact of a fire is, right? Of course, this is not because there are more firefighters, right? It's because the bigger fires attract bigger teams of firefighters, right? So the causation is actually opposite, right? You also have other examples that discuss how the more policemen you have in a city, the more crime you have, right? Of course, again, the causation is opposite, right? When there's more crime in a city, the government is going to send more policemen to that city, right? So these are obvious examples that can be funny even, but lots of mistakes are made, right, with that. And there are even highly published and highly cited studies that get things wrong in a sense, that reverse causality, for example. A more subtle example might be if I ask to you the question, do you believe that older people, if they move more, they are in better health, right? And I assume that most people would confirm that, right? And there's also plenty of studies who show that, right? And yet we need to be careful with that interpretation, right? Because finding such a result. So if you, for example, do a study where you check people above 65, for example, and you check the amount of exercise that they get, and you check their general health, then you will find a very strong correlation, right? A positive correlation. Now, the interpretation of that can easily be mistaken because you might easily conclude that the more people move, the better in shape they are. But this might simply be the result of a selection effect, right? Where it is only the people that are in good health that are still able to move and to exercise a lot. Right? So the causality might actually be reversed. And this is already a more subtle example, right? Now, I do believe that exercise is good, right? It's just to illustrate how you need to be careful with conclusions, how you need to not jump to conclusions, right? So causality and correlation are two different things, right? And it's important to distinguish them from each other. Comparison is also important. It's important to compare your treatment with a control group. Harshit Gupta, you have a question? I see. Go ahead. You cannot unmute yourself.
Yeah, team, can you
Okay.
unmute Harshit?
So my question is that you have already established that causality does not mean correlation and vice versa. But then the question is, what kind of metric should we look into, and what kind of point of interest should we look into in the entire data set to avoid this kind of discrepancies, in terms that if we have established a hypothesis and we are getting different kind of postulates to our hypothesis, but then in order to reach the exact pinpoint where we can conclude the data, right, to actually prove a hypothesis, what should be the metrics of analysis at that particular time? Because we can take a lot of data which is actually not related to our subject of interest. Then how should we cut short, or how should we actually target our data set in such a way that we can prove our hypothesis with much more effectiveness and less discrepancies?
Yeah. So the answer is you cannot through analysis. You have to go to the design of the data collection and see whether that data collection was designed to show causality, right? And that's why it's important to consider design separate from analysis, right? As I mentioned on one of the slides, if a design is not good, you simply cannot demonstrate causality with no matter which analysis you use, right? There are some ways of also providing evidence for causality also in cross-sectional data. You have Granger causality, for example, that you can use on data that was not harvested in a setting that that is an experiment, right? But in like almost all cases, it's impossible to prove causality if the experiment or if the study setup does not facilitate that, right? So in the data, there's nothing you can do. It's in the collection of the data that you need to do that. Okay. So comparison is a second thing that I wanted to mention, right? It's very important to have a very good control condition for your intervention, right? An intervention means that you do something to your subjects, and it's important to compare the effect of that to another group of subjects to which you do either nothing or something different than the experimental group, right? And thinking about that comparison is again very important. And the most clear example that shows that relevance is placebos, right? Or the use of placebos. You could think of testing a new drug on people to cure some kind of disease. So let's say that we develop a drug for COVID, right? Or for depression, even better, right? So we develop a new drug, and we're going to test the effectiveness of that drug. So we're going to give 200 people that drug, and 200 other ones, patients as well. We're not going to give them that drug, right? And you find an effect. You find an improvement in the people that receive that drug. Even if you find that, it is difficult to claim that it's the active ingredient of that drug that caused that effect, right? Because plenty of research shows that merely giving a pill to people improves their depression, no matter where there's an active ingredient in that pill or not, right? So if you want to know whether an active ingredient in a pill works, then the comparison group should also receive a pill, but then without that active ingredient, right? So you should be very precise in what is your comparison. And that's the relevance of using placebos, right? The comparison is not in a pill or not, but the comparison is a pill with a new ingredient versus a pill with no ingredient or a pill with an old ingredient, right? Those are relevant basis or standards for comparison, right? And again, this is something in which many mistakes are being made, right? So that's why I also mentioned these different fields, right? With a different fertilizer, for example. Don't just try a fertilizer on a field to see whether it works, right? cut your field into different pieces and then use your fertilizer on one piece and not on another piece, or a different kind of fertilizer on another piece, so that you have a strong basis of comparison, right? Because who knows what the weather is going to evolve like, who knows whether your soil plays a role into how your crops are growing. You need a strong basis of comparison, right? Very important in experiments and in causal inferences as well, right? I'm going to skip this slide because I see that I'm not doing well on time. Control is then the third C, right? If you think you found an effect of the cause, the independent variable that you're testing on your dependent variable, you need to be sure that this effect is not explained by, for example, a third variable that you did not observe, right? So if you have people taste Coke versus Pepsi, for example, if you ask people whether they prefer Coke or Pepsi and whether they can distinguish between the two, most people will answer yes to that second question, right? Most people have a preference for one of the two, and most people strongly believe that the taste of that preference, of that preferred beverage, is better than its competitor, right? And so if you show people a can of Pepsi and a can of Coke and you have them taste those two, then they will definitely say that their preferred brand tastes better, right? Except research shows that people are actually not at all that good at making the distinction, right? If they don't know what the brand is. So if you blindfold them while they are tasting, for example, if you don't provide them information about which brand they are tasting, they fail miserably at distinguishing those two drinks from each other, right? And so this is an example of where you need to make sure that what you're measuring is an effect of actual taste and not of people's knowledge about the brand, right? This might be a third variable that you did not consider in your experimental setup that fully explains the results, right? I'm seeing another question about the placebo pill. Yes, people significantly improve in health based on placebo pills and even placebo surgery, right? There's research showing that, and this goes pretty far, and again, the ethical aspect comes in there, but there's research showing that people that experience knee pain, putting them to sleep, making a surgical cut in their knee, opening that knee, doing nothing and closing that knee again, significantly improves the condition of their knee, right? So the mere belief that people underwent surgery, even if the surgeon did nothing that should improve their condition, improve these people's condition in a sense that they feel that their knee is better, right? So this is how strong the placebo effect is. And in fact, there are estimates that about 30% of the effectiveness of traditional medicine is explained by the placebo effect, right? It's not explained by active ingredients that have an effect, but it's merely explained by the fact that people believe they will get better when they take a pill or they put some ointment or they undergo some kind of treatment, right? It's a very, very, very strong effect. Yeah. So an effect that you need to control, right? Control is crucial. And so what control is about is making sure that you manipulate one variable of interest to see whether it affects your dependent measure while keeping everything else constant between your experimental groups, right? Now, keeping everything else constant is extremely difficult, right? Because there are so many variables to consider that it's very easy to miss some variables, right? So what very often is being done is random sampling, randomly attributing people to the different conditions. So, well, in the assumption that if your sampling is really random and your attribution to the groups is really random, that there will be no systematic difference between the groups in any variable, basically in any variable, and especially not in variables that could create an effect on your dependent measure, right? It's a strong assumption, of course, but it's the only way of trying to control the entire collection of potential variables out there that could have an effect. It's both. No, it's random sampling and randomization between conditions, right? Both are important. Random sampling is important to have a representative sample, and random attribution to conditions is important to eliminate effects of confounding variables. Right? So based on all of these things, we have to select a research design that is as strong as possible, right? And one of the decisions that we need to make is who is our unit of comparison, right? And one decision that you can make in that sense is whether you are going to control, whether you are going to compare the treatment group with the same treatment group without the treatment, or whether you are going to compare the treatment group to a different group without that treatment, right? And this is the difference between a within participants or within subjects design and a between participants or a between subjects design, right? In the within participants design, people are their own controls, their own control group, right? So you could do this Coke versus Pepsi taste test, right? And then people will rate one of the two drinks as better. And you have basically a within design because you compare the two ratings for the same people, right? You could also try to answer the question like, what is the actual better tasting drink, right? And for that research question, you might as well compare between different people, right? So you might give Coke to 100 participants and then Pepsi to 100 different participants, right? And a conclusion can be made about which drink on average is appreciated more, right? There are different advantages and disadvantages to using those two, in a sense that you have more power in a within participants design. So you need less participants to find similarly strong effects. But your internal validity for between participants design is often higher because you make it less visible to participants what your research setup is, right? And so this means less bias in their responses very often, right? So that brings us to how to analyze experiments, right? So I have another question to you. Which statistical tests can be used to analyze experiments? Any ideas there? And then it went silent. You guys can vote, right? Or okay. T-test, chi-square, correlation, ANOVA. Yeah. So people more or less agree. Regression is now added. Chi-square is people's favorite. No, t-test is people's favorite. Any other? Correlation. Paired and unpaired t-test, yeah. Any kind of comparative analysis, basically, true. Yeah. Okay, so it's true, right? We have a quantitative dependent measure, which can either be data that are on a ratio scale, on an interval scale. We can also have count data, right? If you think about these conversions in A/B testing, for example, these are percentages of people that click through to something, for example. Basically, the answer is that we can use many tests, right? Correlation is not the best candidate, right? Because that shows you covariation between two variables. We really are testing for differences based on the manipulation, right? Because what we assume in an experiment is that our manipulation creates a difference in the dependent variable, right? Now, to analyze that difference, we use tests to come to a conclusion about what we accept as true based on the data, right? And in experimentation, this means concluding whether your independent variable or your manipulation created an effect, a difference in the dependent variable, right? And if that is true, then you conclude that any difference in the dependent variable is not due to chance, but it is due to that manipulation, right? It's important to realize that dependent measures, like any measure, vary, right? There is always some error in your measurement, some variation. And so what your statistical test will tell you is whether that variation is due to your intervention or not, right? Whether this is within the normal variation or whether there's a difference that is large enough to conclude that it is not due to chance, right? So how to decide whether something is due to chance or not? Well, let's see, right? Let's say that we have an A/B test for a website, and this time we're going to measure how many seconds people stay on a landing page, right? And let's say that in a control condition, people stay for 4 seconds on the landing page, but due to some variation that we create in an experimental condition, people stay longer, right? So let's ask ourselves, what is long enough? Let's say that we run 2 different tests, and in 2 different setups. In one setup, the difference is between 4 seconds in the control condition and 6 seconds in the experimental condition. In the second setup, the difference is between 4 seconds in the control condition and 7 seconds in the experimental condition. What I would like to ask you is to use the reactions to give your idea. So you guys know how that works, right? You can send a heart or something else, right? So everybody that thinks that the left result is less due to chance, send me a heart, please. And everybody that thinks that the right result is less due to chance, send me, I don't know what other reactions we have, this party thing. Or a thumbs up or something like that. So a heart for the left one and something else for the right one. I see some party things. Mostly party things, right? And that's the correct answer. So the result on the right is less likely due to chance, right? Because yes, the magnitude of the difference matters, right? Is important. Now, these are, let's say that these are mean differences, right? Average results between the 2 conditions. Those averages themselves are also due to chance a little bit, right? They are based on your selection, and they depend on your selection. So let's say that the one you see on the left here, an average of 6, is composed out of observations that are the set on the left, right? So somebody stays 10 seconds on that website, somebody stays 2 seconds, somebody stays 9 seconds, somebody stays 3 seconds. On the right, you also see an average of 6, but it's composed out of different observations, right? Somebody stays 6, somebody 5, somebody 7, somebody 6. Those means have some error themselves, right? And we could ask ourselves which of those means would stay more closely to the original mean if we're going to add additional observations, for example, or if we're going to take away some observations, right? What I'm basically referring to is the standard error of a mean, right? Which is related to the variance in the sample and inversely related to the sample size, right? And so the larger that variance in the sample, the more your mean is going to fluctuate as well, right? So let's now compare these 2 situations, right? Where we have results of 2 different tests. So you have a control condition that is composed out of 4, 5, 3, 4 seconds, and an experimental condition composed out of 7, 6, 5, 6 seconds, or the one on the right, where both the control condition and the experimental condition have much more variance. My question to you, which of those two differences are more likely to be significant, in a sense that they are less likely to be due to chance? We can use the heart again for the left one and the party thing for the right one. I already see some hearts, many hearts. And this is again correct, right? In fact, if you put these data in an Excel sheet or in SPSS or R or whatever other software package, you can calculate the, you can do a t-test, right? You can run a t-test and calculate the p-value for those differences. And you will find that the results on the left are significant, almost at a level of 0.01. And the result on the right is not significant at all. The p-value is above 0.20, right? So we see that even the means are the same, right, for the two results. We see that this variance determines a lot as well, right? So it's not just the mean difference, it's also the variance of the underlying data, or the variance, the error in that mean that is important, right? So your difference is more likely to be real, not due to chance, when the magnitude of the difference is larger and when the variability of answers is smaller, right? Which is important to realize also for your design, right? This directly reflects on some things you need to consider for your design, because the larger the noise is on your measurements, for example, the more or the higher this variability of the answers is going to be, right? If your control condition is not really aligned with your experimental condition, again, there is going to be more noise, right? So the better, this kind of shows directly that the better your design is, the more likely it is that you're going to find strong statistical results, right? And so we can see how the magnitude of the difference positively influence your likelihood of finding statistical results, and this variability of answers negatively, right? And we can see this ratio as predictive of your results being significant or not. And it's interesting to see that this ratio is actually the same ratio that is used to calculate a t-test, right? T corresponds to the mean difference between two conditions divided by the pooled variance of responses, or the mean difference divided by the standard error of means, right? And so this standard error, again, is your variance divided by the square root of your sample size. So we can make a couple of conclusions about that, right? By the way, it's also interesting to see how this also applies to other statistical tests, like an ANOVA, for example, where your nominator is the variance of means, right? So that's the difference in means, just like in a t-test, divided by the variance of the responses, right? So that's again this variability of your answers. So that works exactly the same way, right? If you reduce that variance in the denominator by having more clean measures of your effect, by having better comparison standards, etc., you are more likely to have significant results. You will create more strong, significant results, right? I'm gonna skip this as well. So this is just a visual representation of how that works, right? So some conclusions based on this is that increasing your sample size, which reduces your standard error, leads to stronger findings. More control, so less random error, leads to stronger findings. And a clearer control condition that is strongly matched to your experimental condition leads to less random error and therefore stronger findings, right? So again, the properties of your statistical tests are informative about what it means to have a strong experimental design, right? And it's important to recognize that. This was kind of an introduction on experimental design. We can, of course, go much farther, right? But in the interest of time, I won't do that. But this was a very, what I mostly discussed was a very simple design with two conditions mostly and an outcome. We can look much deeper into processes by looking at mediations, for example, variables that are affected by your independent variable, and that explain your dependent measure that kind of are in between those two and explain the process. We can look at moderation. We can look at pretty complex models. By the way, some people mentioned that regression can be used to interpret experiments. Most experiments traditionally are interpreted with analysis of variance and with t-tests, but it's true that recently through the availability of some macros for SPSS, etc., created by Andrew Hayes. So there's this process macro that people have switched much more to regression analysis implicitly without realizing very often to interpret experiments, right? So that's for my part of the session. What I was curious about is your feedback about what you learned today. So I have a last question where you can mention to me what struck you, what you thought was surprising, or maybe not, what you remember from this session. So the votes are open. How to become a billionaire? Who knows? Okay. If that's what you take home from this, then I'm happy. Okay. So thank you for your attention. Just as a wrap up, it's indeed important to think about experimental design before you think about experimental analysis, because this can lead to strong conclusions about causality, right? And you have to think about causality, comparison, and control to have a strong design. And a stronger design can yield stronger statistical results. So that was it. If there are any remaining questions, then do not hesitate. That's what I'm here for. Has ChatGPT affected experimental design in any way? For the moment, this effect is limited, I think, except maybe that some people are starting to potentially use ChatGPT for generating vignettes and stimulus material, right? So if you want to test a concept like, let's say that you want to see how people react to different kinds of Facebook posts, right? That all differ in some kind of quality, then it might be useful to have ChatGPT generate lots of Facebook posts of a similar kind to show those to people and to see how they react, right? But for the moment, there's no, outside of that, I'm not aware of any strong impact yet. Other questions? Can I comment on time series data and how experimental design can be best achieved in this case? So I mentioned Granger causality earlier, right? Granger causality is a technique that people use to establish or to show causality in time series. Thank you. where so you observe a phenomenon throughout time, and then if you see that phenomenon change, then you might try to relate that change to other variables that you observe. And Granger causality is a way of doing that, even if a set time series data is not designed to be experimental data, right? So very often these are things that you can only observe, on which you cannot intervene, to which no manipulation is possible, right? That are out there. And then it's difficult to establish causality, but there are some techniques, right? But I again go back to it's important to design your data collection in a way that it can serve causal interpretation of the findings. This is key.
Sir? Sir,
go ahead. Yeah.
I have a question that, as you have mentioned, that it is good for us that we have more amount of data with us. We have a bigger sample that would be good for us. But what in a case that it is not available, like we cannot have a bigger sample, then do we have some measures against it that still we can make our experiment more statistically significant?
So what is always important is to let the data speak for itself. And what is a simple truth is that the smaller your data set, the less that data will speak, right? The less strong your conclusions will be. Now, there are some ways of accommodating small samples. For example, the more and again, I go back to the same thing. The more controlled the environment in which you collect those data, the cleaner those data will be, right? So the more control you have, the less you need a large sample, right? Because you have less random error on your measures. You have a cleaner effect of your manipulation. And so the better your experimental design, the lower the need for a large sample, right? So that's a way of accommodating small samples, or of still finding conclusions in small samples. Other ways can involve measuring lots of control variables, in a sense that you measure additional variables that are not necessarily the focus of your research. And you use that information to basically clean out the effect of your independent variable on your dependent variable. So basically, you kind of isolate that effect by statistically taking away other influences from the environment, right? So if you have a small sample, in a sense that you have not many data not many subjects, it's important to collect as much data as possible from those subjects, right? It's important to measure more variables, including some that might not be your variables on which you focus, right? That are not focal in your research, but you can use those variables to kind of control the environment more.
Thank you, sir. Okay. Sir, I have one more question.
Go ahead.
Sir, on the subject of an experiment being ethical, I mean, being ethical is such a subjective term. How do you measure it? Like causality and all these things are pretty objective. So on that, I wanted to know.
Ethicality is not objective. That's true. And so the usual way to deal with ethicality of research in general is to have many schools have what we call an IRB, a review board, where people judge the ethicality of certain experiments and research in general, and give approval or not for those projects, those research projects, because there is no objective way of saying that something is ethical or not. This is something that is subject to human decision, right? And that is extremely context dependent. Some things that were ethical 20, 30 years ago are not today, right? We we come from a history where let's keep it in my domain, where Coca-Cola was advertised as a good drink for babies, right? For example, or doctors advertised smoking, right? Things like that. What is ethical and not changes depending on culture, depending on time, and things like that. And so there is no objective way to determine this. There is only human judgment in that. And what is best is to have some kind of consensus supporting that, right? You deciding whether something is ethical or not might be highly subject to your personal biases, and everybody has personal biases, right? So it's best to come to a group consensus that decides on whether something is ethical or not.
Okay, thank you very much, sir.
Sir, how can I contact you? I'll share my email address in the chat. If you have specific questions, how can we ensure that our control does not introduce a bias in our conclusions? Well, by the cautious use of that control, right? Controlling should be about keeping conditions similar between a control condition and an experimental condition. Control should be applied in a way that does not create an additional effect, and that's what I think is your question about. I get a warning to leave the meeting. I won't leave the meeting, I think. Let me try to cancel that. So this is by being careful, right? Control is not controlling in a sense that you are manipulating people or subjects in general, right? Control means that you control the environment in a sense that you make sure that there are no other influences on your subjects than the one that you want to be there, than the one that is your manipulation, right? And so your manipulation is controlling the environment, and the rest of your control you should use to keep that environment as constant as possible between your experimental and your control condition, exactly to avoid that there will be a bias in your conclusion, right? If you manage to keep that environment exactly the same between the control and the experimental condition, that's the way of avoiding bias, if that's an answer to your question. Okay. I'll share my email address.
Hello.
Hello.
Hi, sir. So the session was good. It was insightful, and especially you came at the time when we about to start our project. So it was good session.
I'm happy to hear that. Thank you.
So I had a question previously that I asked. It is about the experiment. So how to do a safe experiment. So I wish to learn it more from a small business side. So if I put an example, like a person is selling fries in the market, and he has a competition around it. So and he wished to increase the price of the fries for two bucks, and so it might happen like the people wished not to come to this fry shop and went to other fry shop.
Yes.
So now it's a small business. He cannot afford to do a large experiment or experiment somewhere else that he has only one shop.
Yeah.
So I wish to learn like how he can go about to have a safe experiment. But since he has only one shop, so how he can do it on this shop only? And
yeah, first thing I want to answer is that experiments are no panacea, right? They should not be used for everything, right? And if that business is very vulnerable in a sense, it's a small business, a person's livelihood depends on it, there's no room for error, then I wouldn't start experimenting, right? Then you first need different kinds of data collection. And then what I would personally do is, for example, look at competitive businesses, what their price setting is, and see whether there's actually room for improving, increasing the price or not, right? Look at the market conditions and collect data about that, right? Descriptive data even. And then if you are, if you have enough basis for deciding that there is probably room for a price hike, then you could experiment by experimenting with loyal customers, for example, right? By taking a small sample from your customer base, not increasing the price immediately, but by testing with them whether they would be ready, potentially in return for additional service or something like that, to pay more to that business, right? So it's important to realize that in this case, experimenting might not be the best way, because experimenting means that you already changed that business, right? And if you change that for worse, and if a person's livelihood depends on it, then this is not a good outcome, right? Does that answer your question? Okay. There was another question. Wait. When multiple interventions are involved, should the individual intervention be shown statistically? Both, right? So this is what I mentioned at the end, where we were discussing more advanced implementations, right? So it is possible to implement multiple interventions at the in one experiment, right? At the same time, basically. But of course, you also always need to think about your comparison groups, right? So if you do that, then it's important to realize a couple of things. First of all, you are doing multiple tests at the same time. So you need to apply some kind of correction for multiple testing, right? As you know from your statistical background, if you have a p-value of 0.05, this is just for one test, right? Now, if you do 20 tests, to make it a little bit simplistic, you're going to increase your chance of committing a type 1 error, right? Of making a conclusion that you should not make, right? And so if you do multiple testing, then you need to apply some correction for multiple testing. There are several ways of doing that. In the context of analysis of variance, for example, you can apply a Bonferroni correction, where you simply divide your alpha by the number of tests that you do, for example, right? So this is something that you first should be conscious about. That, let's say that you create some very complex design and you're going to run 100 tests on that design, right? You're going to compare 100 different conditions to each other, for example. Some of your results will be significant, even if a conclusion about those results being significant is not warranted, right? Because these significant results could simply be there based on chance, right? We're still, p-values are probabilities, right? So we could still be making mistakes, right? Even if we have significant results. So that's first something. Second is to understand that the effect of one intervention might depend on the effect of another intervention, right? So once you start combining variables in an intervention, it's important to not just look at individual effects of variables, but also to look at combined effects, at interaction effects of variables, right? Because they might fully explain, or might even better explain some of the findings that you can conclude on, right? I have here an example that is quite a simplistic example. So we were looking at the effects of a price difference, right? To understand the process behind people's changing attitudes towards price difference. We might also look at cognitive load, right? The extent to which people's mind is occupied with, I don't know, worries that they have, things that they need to remember, things that they have on their mind, right? And if that cognitive load is high, then a price hike might not make a difference, right? People might not notice even that price hike. If their mind is empty, if there's a low load on their cognition, then they might notice that price hike, might think about it, and might change their attitude accordingly, right? So sometimes, so this is an interaction effect that you see here, right? This small graph that you see here shows that an effect is only present in a low price condition between high cognitive load or low cognitive load. You could also look at that the other way around. You could also conclude that a difference in price only creates an effect in the low load cognition, right? Because that's the comparison between this point and this point, right? So that's an example of an interaction effect where you include two, in this case, variables as independent variables, and you look at their combined effects on an outcome, which in this case is attitude. So you need more complex models for that. You need an ANOVA that includes an interaction effect, and this can go pretty far. You can have two-way interactions, three-way interactions, four-way interactions, etc. And they become increasingly difficult to interpret, but it is perfectly possible. Is that answering your question? How to group similar customers based on spending habits. Okay, we're going to close the session. I also read in the interest of time. Okay, then let's close the session. I just want to say that I had a lovely time here. I'm happy to have been given the opportunity to present for you, and thank you for all the interesting questions and the nice feedback that I read as well.
Thanks a lot, Bart. I mean, it was really, really nice, and I think students also enjoyed it. So if anybody would like to share closing remarks, 2 or 3 of you, so that's it. With that, we would be closing it. Yeah.
Okay.
Anybody would like to share the feedback, or how did you actually like the session and how it was?
I'm reading some
comments. Yes,
some nice words in the comments. So thank you all for that. And I wish you a lovely evening then.
So Professor Bart, yeah, it's a very good session. Yeah, I am from mechanical background. I've done my PhD. I'm an experimentalist, so I can correlate a lot of things actually from your lecture. So it's a quite insightful talk, and I hope a student enjoyed the talk with a lot of examples that they can correlate with their real life situation. So yeah, it's very nice.
Thank you for those nice words.
Thanks.
Okay.
So anybody else would like to say something? Tanuja, would you like to say something?
Since I come from an IB curriculum, I have already had a lot of interaction with, experimental design, and it really took me back to my 11th and 12th grade time, and I really enjoyed the session. The fact that it was interactive really, even though it was quite a long session, I didn't feel that like how fast the time went by. Thank you so much.
Okay. My pleasure, and thank you for those nice words. Okay. And I hope to maybe indeed interact more with you in the future.
Yep. Thanks a lot, Bart, and we look forward to hosting you again and take more sessions, and maybe have subjects from you floated as well in the future. So thanks a lot, and thanks a lot once again, and we'll close it. Thank you. See you. Good night. Bye bye.
You too. Bye bye.
Bye bye. Bye bye.